Hello, my name is Gehad Youssef, and today I will present a short talk entitled Medical Text Classification using Dynamic Time Warping and a CNN Bidirectional LSTM Hybrid Model. This is our preliminary findings for the DILI challenge. One of the challenges of the drug discovery pipeline is to identify side effects of drug compounds early on in the drug screening process. One such relatively common side effect is DILI, which stands for drug-induced liver injury. This year's CAMDA challenge involved giving us midline abstracts, and we had to classify them into DILI positive and DILI negative. The DILI challenge was set up in the following way. We were given abstracts or titles that were either positive or negative DILI, and we had to submit our predictions for the first validation cohort of 14,210 and then the second validation cohort of 2001 abstracts. We approached the DILI challenge by conceptually formulating text data as time series data. And by using deep learning models, we're able to consider the sequence and structure of that data, and we can even align the data as one would align time sequence data. We split the data into two sets of balanced cohorts. The first one, 8,000 positive and negative DILI abstracts, was used to develop our models. We use a 90-10 training testing split and use these three random seeds, 15583 and 1443, and took the average of these. And then in the second balanced cohort, we derived the confusion matrix. Then when we were ready to submit, we submitted our predictions using for the two validation cohorts. We processed the data in Python. We used a fairly standard pipeline in this stage. We merged the titles and abstracts into one column. We did the initial processing of the data using the GenSim package, and then we obtained sparse, highly dimensional representations of the text using Count Vectorizer. We had 25,180 features. The term frequency inverse document frequency TF IDF representations were also obtained using TF IDF transformer, and then we did the fairly standard text embedding, padding and tokenizer steps. I just want to point out that for most of the models, whether it's SVM, naive Bayes or DTW, we use the TF-IDF representation. But for the deep learning model, we use word embeddings. This came just as a process of optimization. We tried various permutations, and this was the best optimization. We used a tiered prediction strategy. We developed a majority vote using the CNN-BiLSTM hybrid model, the SVM and naive Bayes classifiers. We then had two outcomes. We had a stable prediction outcome where there was complete consensus in whether the abstract was DILI or not DILI. If there was a discordance in the majority vote, we then use dynamic time warping as a method of conflict resolution by taking the 0.5% most aligned abstract. If we still fail to get majority vote, we can expand that to the 1% most aligned abstract. This is just a schematic reminding you of how dynamic time warping would work. The rationale behind looking at stable and unstable predictions and then using DTW alignment on just the unstable predictions was because of the following observation. If you look at the DILI and non-DILI abstracts and look at the percentage of the percentage of stable predictions that were correct. So in this case, DILI correct stable predictions 92.2%. Non-DILI was 82.66%. stable correct predictions. But when you consider the unstable predictions, you get, in the case of non-DILI abstracts, 14.33%, whereas DILI abstracts had 6.98%. If you just take the unstable predictions and compare the performance of DTW alignment with the simple majority vote, you will get a higher accuracy with the with DTW, 89% compared to 84%, and the total pipeline, when including DTW, would be 95% in our internal validation, compared to just a simple majority vote of 90%. So this was the rationale why we would use DTW instead of just taking a majority vote. The result of the first validation cohort produced an accuracy of 90%, but with a significantly higher recall of almost 0.94 compared to precision, which was 0.87. In order to try to improve the precision score, we expanded the majority vote members to include the stochastic gradient and k-nearest neighbor classifiers, but we still kept the DTW algorithm as a conflict resolutor. However, unfortunately, that just led to overfitting, as we did keep the recall high, but we lost a lot of the precision. So we unfortunately did worse off in the second validation cohort than the first validation cohort, suggesting that we should not have expanded the majority vote. So in summary, what we proposed here was incorporation of hybrid machine learning classifiers with dynamic time warping, and more conceptually to treat text data as time series data. We are still exploring different permutations of introducing DTW with the machine learning classifiers. For example, even our threshold of 0.5% of the best aligned abstracts, that's arbitrary. That's not something that is set in stone. So we need to explore this further. We want to also extract the top features, especially from the stable predictions, to maybe develop better interpretability models.